there is a question when you deal with crack propagation criterion, you said that my K1 have to large than K1C, the crack will propagate. It does not deal with the question of what happened when your crack start to propagate. Okay, there are scenarios. Could have two scenarios when your crack start to propagate. One is your crack will propagate for some time, and then when the energy is spent on generating the surface, it will stop propagating, right? And another case is when you have the crack will propagate, and then the crack will continue to propagate. It will not stop, and then it just crack the whole body. So one example is probably, I don't know how many of you guys are from cold places. Anyone from cold places? I mean, anyone who walked on ice on a lake? No? That's a bad example. One example is, for example, in winter, if the ice freezes over or the water freezes over on the lake, and then usually early spring you start to, in winter maybe you have no problem to walk on the ice. You can even drive on the ice. But sometimes around this time is when the kind of the danger part is you don't know whether the ice is strong enough. So you can start walking and then you hear the ice crack, right? And then you will be like, okay, should I continue walking or should I stop? If you stop the crack, and that ice could also break too. So basically you hear the crack. What that means is there's a crack formed in the ice. But sometimes you just hear the crack and then nothing happens. Right? You can continue walking. But sometimes the crack, the ice will cave in and you are in the water. So that's two cases. So that's what we call crack propagation stability problem. So this deal with once the crack start to propagate, what happens? If you have a stable crack growth, it doesn't mean that the crack growth is stable, is constant. What it means is that the crack will propagate for a certain distance. And then it stops. And so that actually is a good scenario in a bad scenario case, because at least you will not break the part and causing other subsequent damage. So in this case, you know that your crack will propagate, but it will stop, so that, and also hopefully you will notice when the crack propagate. So now you can take some repairment or double check it and something like that. So this is equivalent of you walk on ice and you hear the cracking, but you are not in the water. That's the best case scenario, right? So for unstable crack, crack growth unstable. Is that in this case the crack will continue to grow once it and that of course eventually it will lead to the fracture of the part. So that's the scenario you don't want to be in, because this is equivalent of you hear the crack, the squeaking of the ice. The next thing you know, you're in the water. So that is definitely a situation you want to avoid. So the question then is, how do we determine whether the crack, once it starts to grow, the crack will be stable or unstable? So the criterion, again, we have lots of criterion in fracture mechanics, is that the crack growth is stable when the system energy at an equilibrium is maximum, and the crack growth is unstable when it's linear. So you probably have seen this in math also. Basically, if you draw, this is actually very visual. So this is, the x-axis doesn't matter. So assume you have a curve like this, that's your strain energy. If you are over, wait, did I have it the opposite? My note might be the opposite. Yeah. This is unstable, and this is stable. Okay. That makes much more sense than before. Okay, so the crack growth is unstable when the system energy at equilibrium is maximum. So basically you can think of, you have your strain energy look like this, and then if you have, so basically a heel, if you have a ball on top of the heel, is that stable or not? It's not, right? So you kind of poke on it, or you move it a little bit away from the equilibrium, it's going to fall down the hill, right? If it's over here, where your strain energy is the minimum, even though you disturb it or perturbate it a little bit from the equilibrium position, it's going to come back to the equilibrium position. So that is a stable condition. So this is stable, and then that is unstable. Okay, so put that into equation. Is that your total energy, which is your potential energy, plus your gamma, which is the surface energy, over the area. If it's less than 0, it's unstable. And then if it's larger than 0, it's stable. And then it's equal to 0, is neutral. So that's basically for the strain energy method, there's an advantage in this case as compared to the stress intensity factor is you can, once you find the strain energy and once you know how the surface energy behave, you can actually predict where the crack propagation will be stable or unstable. And of course that is a big plus because it's okay sometimes as long as the crack propagates as long as it's stable, right? The thing that we want to avoid is the unstable crack growth that happens very fast. G, the strain energy release rate is d pi over dA. So that essentially you can consider that's your driving force or driving energy for crack propagation. And then your gamma, of course, is the surface energy. I should put it over here. This is the strain energy release rate. And your surface energy is d gamma over dA. And that essentially is the resistance. So that's why we sometimes represent it as an R, and that's the resistance to crack propagation. So if you go from here and then you replace those two parameters with these, and so what you get is you take one derivative, so you take a minus. And so from that, so this is basically different steps to check that whether the crack propagation is stable or not. You can go straight from here, take second derivative, or you can just go from here and take the first derivative. So, but that is essentially the same, just a reverse of sign. So if this is larger than 0, then it's unstable. If it's less than 0, it's stable. And then if it's equal to 0, it's neutral. Sometimes, depends on the material, for the R, sometimes it's constant and sometimes it's not. So if you have a material is equal to the resistance is constant, what that means is the resistance to crack propagation does not change with crack length. Right? So for some, is the crack propagate and you need to apply more load or to make it propagate again. For some, the resistance is independent of the crack length. So that means that UGR over dA is equal to 0. So obviously, you go from there, then now, if that is the case, then you can base on the strain release, energy release rate alone to determine whether the crack will propagate or not. So if this is larger than 0, then that's unstable. So that's basically 3 different levels of how you can check whether your crack propagation is stable or not. So the question is, obviously, we know how to calculate the potential energy, which is related to work done by the external force and the elastic energy. The surface energy is depends on by the material. So that you have to come up with some experiment to measure it.